Hi, cutie patootie math angel. Welcome back and welcome to Decaf-Math ASMR if you are new around here. So today I thought we could look at two examples that are very similar but a little bit different. Examples of sine substitution, which is one type of trig substitution. So trig substitution is a technique that we can add into our toolbox for finding integrals. And I think we've worked out an example of a trig sub at some point, but I've gotten a lot of requests for this, so I thought that we would start with the sine today, but we can extrapolate everything we talk about today for tangent and secant. And so let's take a look at the two questions. And the first one is sort of the most classic, basic trig sine substitution. So let's start with that. Which looks like this. Finding the integral of 1 over the square root of 1 minus x squared with respect to x. And so this is the first question we'll look at, and then the second one's going to look a little bit different, but you'll notice it has the same form. So we're going to do the square root of 9 minus 16 x squared. Okay? And then down the line, after we build some intuition, we can work out more complicated sine substitutions, but let's take this step by step. As always, though, I should mention it doesn't matter whether or not you're actually learning this, and if you even like math or hate math or whatever. I'm just glad that you're here right now, and I encourage you to just relax, hang out. I'll do my thing, you do yours, and if your eyelids get heavy, feel free to just drift off to sleep or just zone in and out as you please. But if you are learning this, I hope that you will be kind to yourself and take your time. And so, nothing formal or anything, and if you are looking for a quicker tutorial, this is probably not the right place for you. We're just going to do this in layers. So that's what we're all about today. So the main idea for trig sub is that we have a bunch of tools that we've already talked about for integrals, right? Like we have our basic integrals, which are kind of integral counterparts to our derivative rules, right? So the integral of x to the power of some number is going to be x to the n plus 1 over n plus 1, this kind of thing. So our basic integrals, like the derivative of the natural log of x, is 1 over x. So the integral of 1 over x is the natural log of x plus c if you need that. And so we have our basic integrals, and in this case we can't do that because unfortunately we have this square root over this whole thing, 1 minus x squared, and you can't separate out the square root or anything, so you can't really simplify that. And we've also talked about U substitution, which is where we try to simplify this whole thing in terms of U. So we change a variable. So we might, let's say, try to set u to equal 1 minus x squared so that we'd have the square root of u, which might just be easier to deal with. But the problem there for this case is that if I let u equal, let's just write that out, if I let u equal 1 minus x squared, then my du is derivative of this thing is negative 2x dx. The 1 goes away to 0, so negative 2x dx. And I don't have a factor of x here, right? I don't have an x up here, just the derivative with respect to x, but no x here. So I can't use u sub. And we've also talked about integration by parts a bit. So that's our u and v and dv and du stuff. But in this case, maybe we can do that. It would be very complicated if it did work, but that we would just put to the side here because it's not clear. There's not a lot of factors to work with here. We have like a 1, so I don't think that that would necessarily work, and if so, we might have to do it multiple times. And so we've also, well, I don't think we've talked about it directly here, but you can actually also use or try to use partial fractions. If you have fractions here, you can try and split it up into pieces and then take the integrals of those pieces. But in this case, again, we have a square root thing going on, so that makes it a little inconvenient. So all that being said is those are kind of in the order of simplest to more complicated. But if none of those work, then, and you notice that there's this kind of form here, this special kind of form, then trig sub is something that we can kind of add to our toolbox. So what is our goal here? Our trig substitution actually makes this thing, whatever we're integrating, more complicated for a second. So it's like, why, with U substitution, I try and simplify this. I try and let maybe U equal 1 minus x squared and condense it all if it works. But for trig substitution, I actually let x be something with a trig function in it. And so this is actually going to expand out, which seems kind of weird. But if we're clever with how we pick our x, what trig function do we use, and what kind of coefficients are we using? If we're clever with that, this whole thing actually ends up simplifying to be something we can actually work with. So it's actually very cool. So that means that we're looking more for the bigger picture form for this stuff. So I know that when we first learn about it, I assume that if you're actually watching this for practice or for review, that you've actually heard of this before. And at first it can seem kind of confusing because you might have heard of like this a squared minus u squared or a squared plus u squared and all that kind of stuff. But really, all this is about is that we want to notice the big picture forms of a few trig identities, few basic trig identities. So the very first fundamental one from our unit circle is simply that sine squared theta plus cosine squared theta equals 1. So we've talked about this in trig, in our trig playlist. And from this, we also have, if we actually divide cosine squared all the way through, we actually get that secant squared theta is 1 plus tangent squared theta. And rearranging this one more time is to move this over. So we actually also have that tangent squared theta is secant squared theta minus 1. And so let me just, for consistency, let me write that cosine from this. If I move sine squared theta over, I get that cosine squared theta is 1 minus sine squared theta. Right, I'm just going to move this over here by subtracting sine squared theta on both sides. So these three are all that I need, really. Because I am looking at the bigger picture form here. So we said that we are going to take this x and we are going to expand it, and if I notice I have this constant number, 1 in this case, 1 minus x squared. Well, if I look at the forms of these, I see that, hey, 1 minus stuff squared. So if I somehow let stuff x be sine theta, well, that would be pretty cool, because then I would have 1 minus sine squared theta, which would be cosine squared theta. And when I take the square root of cosine squared theta, normally I'd have to do the absolute value of cosine theta, because cosine can be negative on our unit circle depending on where we are on our unit circle. But since it's an integral like this with no bounds, we can actually just go ahead and write cosine theta. So we'd have the square root of cosine squared theta. So like we said, we want to be clever in what we pick, and so in this case we can do x is sine theta. Theoretically we could also do cosine, but you just have to include like a negative when you deal with the rest of it. So these are just the main ones that you'll probably see. So that's pretty much it. So that's where the forms, if you've seen it, that's where the a squared minus u squared stuff comes in, is for, let's make a little table here. So let's say we have sine. For sine substitution, if you have 1 minus x squared like this or so, then if you let x equals sine theta, then you have this 1 minus sine squared theta, which would be cosine squared theta. So it might not even be under the square root, but usually that's like the best way. Well, that's the ideal case, because you'd have the square root of cosine squared theta. But just anything of this form in general. And along those lines, you might see this a squared minus u squared thing. And all that is that a squared is my number, and this is my variable stuff. Okay, so like in this case, I have a number squared. It doesn't have to be a perfect square. So if I had like 17, I could have the square root of 17 squared. It's okay. It's just some number minus my variable stuff squared. And we'll talk about the slight adjustment you need to make here for this kind of thing, but we'll talk about that here in a second when we do this question. That's the idea. So all we're really doing is looking at these identities and looking at the big picture form. So I have 1 minus stuff squared, I have 1 plus stuff squared, I have stuff squared minus 1, and these can be reversed, right? I can have stuff squared plus 1. Those two can be switched. So that's why it's most often this sine, tangent, secant. So we'll come back to tangent and secant, but the idea is exactly the same. I have 1 plus stuff squared. Conveniently, that would give me something to do with secant squared theta, which is combines it and simplifies that. So if I have some kind of, 1 plus x squared, or in general a squared plus u squared, or the other way around, u squared plus a squared. Those are all going to be nice x equals tangent theta situations. And for secant, I would have this stuff squared minus 1, so that would be my x squared minus 1 situation, or u squared minus a squared, stuff squared minus number, and that would be a nice secant substitution. And again, you might have some different coefficients, and we'll talk about that here in a second, okay? So that's the idea, is when we look at this, instead of 1 minus x squared, I have stuff squared, 1 plus stuff squared minus 1. Okay, so that's a lot of stuff. But it's more like, what does this form look like? That's what we're really going after. So that means that if I let my x equal sine theta for this question, then let's carry out this entire substitution. Like we said, it expands and gets messier first, and that's okay. So x is sine theta, that means that dx is the derivative of sine theta, which is cosine theta, d theta. And so then we have cosine theta, d theta, right? Instead of dx, now we have cosine theta, d theta. And now we'd have the square root of 1 minus sine theta squared, which we write as sine squared theta, like this. And why did we do this? Why did we make this into this mess? Because I noticed I had this form, 1 minus stuff squared. So if I have 1 minus stuff squared and I let that stuff be sine theta, conveniently, this inside piece is now going to be 1 minus sine squared theta, which is cosine squared theta. So I'd have cosine theta d theta over the square root of cosine squared theta. And like we said, normally I'd have to have the square root of this thing squared is going to just be the absolute value of cosine theta, but it's an open integral like this, so we're just going to leave it as cosine theta. So if your question had a particular domain here, a particular interval, then make sure to adjust. But here we have these two cancel, and we'd have the integral of 1 d theta, or just integral of, with respect to d theta, however you want to do that, however you want to write that for yourself. It's 1 d theta, and so that will just be theta, and then plus c. So that's our answer, but our integral was with respect to x. So now we have theta here. So we want to convert theta in terms of x. So how do we do that? Well, we have x equals sine theta. Sine theta. So that means that theta is inverse sine x. So arc sine x, or just sine inverse x, whichever way you like to write it. But that's it. So this is, our answer is arc sine x plus c. So this is actually the integral of 1 over the square root of 1 minus x squared with respect to x is arc sine x plus c. How cool is that? A simple trig sub allows us to solve something like this into this. Pretty cool, isn't it? And even if you don't think so, you can just tell me yes. Make my night. Okay, so take your time with this, absolutely. I would say first thing is to get very familiar with these identities and make sure that you can see how for expanding things. So we just need these different cases. 1 minus stuff squared, 1 plus stuff squared, or stuff squared plus 1, and then stuff squared minus 1. That's all that it is. You might have learned this in the context of, ratios with right triangles and stuff like that. That is usually for later. So the intuition oftentimes, these identities all come from, the unit circle anyway, and right triangles. But, so aside from, breaking down the actual identities, the stuff with the ratios of that often come with having more complicated integrals with these trig functions. You kind of sometimes need to set it up to find like the, let's say, cosecant of a sine of something, and so it's like a different kind of thing. But the intuition behind this is really just these identities here, because they help us simplify a more complicated integral. And so it gives us intuition behind why we would expand it this way. So that's really all that it's about. It's like, what does this look like? Well, this kind of looks like 1 minus stuff squared. So conveniently, if I let x be sine theta, then hey, look, this trig identity looks that same way. 1 minus stuff squared is cosine squared theta. So, hey, it simplifies. So that's all that this is about. So, let's do this question now here and kind of see what's going on. And there's a few ways to do it, but let's just use this as another example. And then from there, we can work out other sine way. So now let's take a look at this one. So it's very, very similar, but there's a few ways to do this. So you can pick which one you like. So if we have the integral of this 1 over the square root of 9 minus 16x squared. So this is the situation where we have this kind of a squared minus u squared stuff. It's a number constant minus stuff squared. Okay, so the same form, but now we don't have a 1. So you might see here we have 3 squared is 9 and 16 is 4 squared. So we could write that as 4x squared, or just 4 squared x squared. There's lots we could do here. But like we said, it doesn't have to be a perfect square. It's just of this form, some number minus stuff squared. Okay, so to solve this, we can do a few things. First of all, if we, if you like to memorize things, then you might see this. So if you have this particular form, the square root of a squared minus b squared x squared, then you go ahead and you make the substitution x equals a over b sine theta. So in this case, I would let x equal a being 3, not the whole number, but 3 squared. So 3 over b being 4 sine theta. And so the idea here is that when I square this, right, if I square this part, I would square 3 squared is 9 over 4 squared is 16. So the 16 and the 16 on the bottom would cancel, and I'd have 9 minus 9 sine squared theta. We can write this out here in a second, but then I would factor out that 9, and I would be left with the 1 minus x squared, or theta, or no, we'd have 1 minus the cosine squared theta stuff, which is what we, or 1 minus sine squared theta stuff, which leaves us with our cosine squared theta. So let's go ahead and do this. This is for if you can kind of do this in your head and see that if I let this sort of be a fraction now, that I want to be able to have 9 minus 9 sine squared theta. So let's carry out the actual substitution the exact same way as before. So the derivative is 3/4 cosine theta d theta. So I have to still do my dx as this whole thing. Cosine theta d theta over the square root of, and I'm going to write this out step by step here, 9 minus 16 times, we're going to square this whole thing, 3/4 sine theta squared. And as you practice, you won't have to write every single thing out, but it's okay. 3/4 cosine theta d theta up on top. Then we'd have the square root of 9 minus 16 times, and when you square this, it's 3/4 sine theta squared. So it's 3 squared, which is 9, this is minus, over 4 squared, which is 16 sine squared theta. When you have this whole thing squared and they're all times together, 3/4 sine theta, they're all multiplied together. Then you square every single thing. So now we have the 16 and the 16 cancel, go away, and you have the integral of 3/4 cosine theta d theta, and then you have the square root of 9 minus 9 sine squared theta, which you can actually factor. So you can do this, and because of a property of square roots where you have multiplication, you can pull this 9 out to be a square root of 9 is 3. So you'd have 3 cosine theta d theta, and I'm going to go ahead and move that 4 down to the bottom. Just be careful with your fraction work there. It's okay to do that. And so then you'd have the square root of 1 minus sine squared theta, which is the exact reason, exact same thing from before with our 1 minus x squared. So now we have our 1 minus sine squared theta because this thingy becomes cosine theta again, and these 3's cancel. So we now have cosine theta d theta over 4 cosine theta. So all we did was made a slight adjustment. It has the same kind of form, right? So we have the square root of some kind of constant minus stuff squared. Constant minus stuff squared. With this slight adjustment here, we just do the a over b sine theta. So cosine goes away, so we're left with 1/4 d theta, which is our 1/4 theta plus c. Very nice. So now we do our theta. Again, our answer should be in terms of x. So we had x is 3/4 sine theta. So then we divide by 3/4 or multiply by 4/3. So we have 4x over 3 is sine theta. So that means theta is arc sine. Arc sine. 1/4 arc sine of 4x over 3 plus c. Ta-da! So, oops, I didn't realize it was all cut off here. But all I was doing here was to solve for x. So, theta, theta in terms of x. So, I did theta, sine theta is 4x over 3, so then theta is arc sine of 4x over 3. So this looks very similar to our first one without the constants. We still have an arc sine, but now with the influence of a and b values, or this number minus stuff squared with these coefficients, our answer is slightly different. Now we have an arc sine, but we have 1/4 and 4x over 3. So the 4 and 3 are definitely from this this 9, and 16 being 3 squared and 4 squared. But no need to memorize this form here, just really recognizing that all we're looking for is 1 minus stuff squared is enough. And then, you can memorize this a over b sine theta if you want to. Again, the idea is once you square it, you have a squared on the top and then b squared on the bottom, so the b squareds cancel, and then you can factor out an a squared, and then get the other stuff, the square root of 1 minus sine squared theta. So it's still a sine substitution here. So the last thing that I wanted to mention was that you can do this slightly differently with the quick little u sub first. So you could do it this way if you want to, and you recognize this a over b sine theta. But you can also actually start by factoring out the 9 in the first place. So if you go back to the original question, knowing that we want to do 1 minus stuff squared ahead of time, because you have a constant minus 16x squared, so this is where recognizing this a squared minus u squared form might be helpful, is that again, trying out all the other methods, seeing that it might not work, you might want to try factoring out this 9 first. So I go like this, 16 over 9x squared, like so. And that way I can pull out this 9 first instead of doing it later here. It's a similar thing, but there's a slight difference. Let's see what happens. We get the square root of 1 minus, and this is actually a perfect square, so we'd actually have 4x over 3 squared. And so we have the 3, which we can actually pull out of the integral, right? One of our properties is to be able to pull out constants, so we'd have 1/3 integral of dx over square root of 1 minus 4x over 3 squared. So we actually kind of have this form 1 minus stuff squared. So this is actually where we can do a quick little u substitution. Let u be this stuff, and this is fine because it's just a constant times x. So du would be 4/3 dx, right, the derivative of this, and so then dx would be 3/4 du. So we can convert this whole thing now in terms of u, which is okay, because now we have 3/4 du over the square root of 1 minus u squared. And then again we can pull out this 3/4 because it's a constant. So 1/3 times 3/4, the integral du over the square root of 1 minus u squared. Very, very nice. And this is really cool. This is really, really cool. Because now this goes away. We have 1/4. And what about this looks familiar? That is just like our integral with our dx and our square root of 1 minus x squared. Except now it's all in terms of u. So our answer to that was arc sine x. Our answer to this is arc sine u, and then plus c. But our u is 4x over 3. So we just have 1/4 arc sine, because we want our final answer to be in terms of x. So just 4x over 3 plus c. And that would be our answer here for this way, which is the exact same as before. Let's see, 1/4 arc sine 4x over 3. 1/4 arc sine 4x over 3 plus c. So the only difference between these two is whether you want to go ahead and memorize this a over b thing if you have like a constant minus stuff squared with our variable. Again, they don't have to be perfect squares. In this case they are, but you can still apply this for other stuff. You can do a over b. Just remember it's the square root of this thing divided by the square root of this thing. And intuitively, let's say you don't have that memorized, but intuitively you just kind of want to divide out this coefficient once you square it, and then you want to factor out this. So you either do that directly and carry it all the way through, or you can just remember that all of our trig identities have a 1, so you might want to factor that out here first. Factor out that 9 so that you have a 1, but then you're going to be left with this stuff here. So then once you have that 1, you can kind of simplify that by using a U substitution. And then just remember that our final answer needs to go back in terms of x. So it's just kind of like an order of operations thing, just depending on your preference. You can mess around with that a little bit. And I hope that this helps, and I hope that it's a nice start. So we're just kind of building intuition behind these trig substitutions, when to use which one. And then we're kind of introducing the idea here. We just did sine, but the idea of factoring first with the U sub, or working it out the other way and just adding little changes here, little coefficients. So you might add the same thing here for tangent or secant. So, but it all just comes down to our identities here and just covering all the situations. 1 minus variable stuff squared, 1 plus variable stuff squared, or variable stuff squared plus 1, and variable stuff squared minus 1, and also their sort of corresponding, a squared, like our little adjustments with our constant squared minus stuff squared from there. And more complicated questions, really, it's all the same thing, but it just involves other, combining trig work together. So that's oftentimes where our SOHCAHTOA stuff comes in, and that's where we want to fill in our right triangle. But the intuition behind this is actually not really from that, aside from the identities being from the unit circle and right triangles. Where it really comes down to is recognizing the forms it kind of looks like these identities. So having them and expanding out for a second actually helps us simplify it, even if it doesn't look like it at first. So that's what I have for this. If you are asleep, I wish you sweet, sweet dreams. You can definitely come back, work on this some more. Didn't want any pressure here at all. We're just hanging out and chilling. So thanks for joining me. And I was going to say something and I forgot. But either way, I hope that this was kind of interesting, relaxing, whatever, good to zone in and out with, whatever you need it to be. I'm sending you much, much love. Do take your time with this, and I'll see you around.